Hello, this is Mr. Wakefield, and we're going to start Chapter 9 right now. And this is the first time that we're going to see variables inside of an exponent. Variables, and that's going to be a big thing in this whole chapter. Variables in your exponent. I'm going to start out as basic as we can here. We're going to look at this thing called an exponential function. And the reason why they call it exponential is because the variable is in the exponent, thus exponential. The most basic kind is when you have, and I want to make this really clear, the b is a constant, you guys. For example, that could be 2 to the x power, or 3 to the x power, or 4 to the x power, something like that. It's a positive constant other than 1. We're not going to do, well, like 1 to the x power. That's something we're not going to do. So it's got to be positive, constant, not 1, all right? And then x is just a normal variable. All right. When that happens, when you just have the constant and the x there, we'll see bigger problems on the back side of your worksheet where we kind of throw some other things in there. But when it's just the constant and the x, for example, if you had, say, f of x equal to 2 to the x, or f of x equal to 3 to the x, or 4 to the x, or any of those different types, the graph will basically look the same. Not exactly the same from one graph to the next, but it'll basically have this shape right here, which I like to call a banana shape. It looks kind of like a banana, but also it looks like a skateboard ramp, if you're familiar with that. Where it goes up really fast on one end, okay, and then it goes down almost in a flat way eventually, and almost flat. It does not completely flatten out. I know it looks like it, but it basically goes down really slow, almost to the point of flattening out on one end, and then it goes up really fast on the other. Sometimes it's the other way around, where, as you see over here, sometimes it goes up very fast on the left, and it goes down almost to the point of being flat over here on the right. So how do you know which one looks like this and which one looks like that? I'm going to talk about that. When the b, that constant base, in other words, when that thing is greater than 1, such as 2 to the x, or 3 to the x, or 4 to the x, or even if you had something like this, even if you had 3 halves to the x, okay, because 3 halves is greater than 1, it's 1.5. Any of those possibilities, the graph is going to look like this. Okay, and it is going to be, let's take a look at that here. It's not just true that it goes up fast on the right and it goes down real slowly, flattening out on the left, but there's some other characteristics I want you to notice. It always has a y-intercept of 1, and I'll tell you why here in a second. There's a good reason for that. It always has a y-intercept of 1, okay? And then the other characteristic, besides the fact that it has arrows on both ends, okay, like a lot of the graphs that we do, so don't forget those arrows. But also please remember that as it flattens out here, you guys, it gets closer and closer to the x-axis without touching it. Now, if you just barely skim the x-axis with your arrow or even with the graph itself, I'm not gonna make a big deal out of that. Just make sure that it doesn't completely cross over down here onto the other side of the x-axis down here. If you do that, then I'll think that you don't understand how it works. Okay, so it's supposed to stay above the x-axis but get really, really close to it. And whenever a graph gets really, really close to a line without touching it, as it goes out either towards the left or to the right, okay, see how to the right it does that same thing over here on this graph? It gets closer and closer to the x-axis without touching it. That makes the x-axis, in this case, what we call a horizontal asymptote. The word asymptote refers to when the graph gets closer and closer to something without touching it as it goes out forever in one direction. In this case, forever to the left, or in this case, forever to the right. So these problems have these asymptotes here, and we need to make sure that the graph does not cross over them. If it just barely touches it, like I said, I'm not going to make a big deal out of that. I know it's kind of sometimes hard to avoid that because it gets so close to it, all right? But make sure it doesn't cross over to the other side of it when you're graphing it. So be careful. So what is the difference between this graph and this one? This one here, it says that the b, the base number, the number that's taken to the power, that is between 0 and 1. So examples of that would be, for example, f of x equal to 1/2 to the x, f of x equal to 1/3 to the x. All right, these fractions right here are between 0 and 1. All right, 1 divided by 2 is 0.5. 1 divided by 3 is 0.33333. Okay, the point is that when the base is between 0 and 1, in other words, it's 0 point something, that means that it is going to be this situation right here. Again, I really want to emphasize, you guys, these two graphs I have right here are only when you have b to the x, not something where you throw something else into the mix like I have in the back here. Okay, we'll get to that here eventually. It's very similar, and that's nice, but it's not exactly the same. But when it looks like one of these things right here where you just have the constant base and just x in the exponent, just x only in the exponent, then it's going to be one of these two graphs, and it all depends on what b is equal to. Okay, so over here, b is between 0 and 1. Again, just like the graph over here, this graph also has a y-intercept of 1 every single time, and it also has a horizontal asymptote that's the x-axis, like we said, and it also has this effect of being really flat almost on one end and going up really fast on the other, like a banana shape. Okay. So let's try this out. Okay, how are we gonna? I mean, we know that that's the basic shape, but here's the thing. All right, yeah, that's the basic shape, but sometimes the graph is really wide. Like it's kind of like with parabolas. Sometimes it's really wide like that, and then sometimes it's going to be much more narrow like this. Okay, so how do you know if it's that or if it's that? Okay, but it's still going to have the same type of banana shape, though. Okay. It's still going to be going up fast on one end and being almost flat on the other. How do you know which shape it is? That's where you have to actually plug in some numbers and find out. Okay, these are the 5 numbers that we're going to use when we do the b to the x graphs, not the ones on the back side of the worksheet. Again, we'll get to that in a few minutes. But when we have just something to the x power, we're going to use these 5 numbers. Let me write that down. So we're going to do, I'm going to plug in 5 numbers here. Okay, and then you have to just figure out what the y is equal to. Kind of like what we did back when we first originally started graphing lines. You plug a number into x, and you figure out what y value pairs up with it by solving for y. It's the same thing. All right, so if I plug in -2, what is 3 to the -2? Well, as you know, when you have a negative exponent, from back in chapter 1, we learned that 3 to the -2 is the same thing as 1 over 3 squared. This is from section 1.6. Okay. And then you figure out what the top and bottom are equal to, since this is just a normal fraction with no variable in it. Figure out what the top and bottom are equal to, and then put it in lowest terms, if it's not already. It's 1/9. And that's already in lowest terms. So our answer there is 1/9. Okay, you might be wondering, how do I graph 1/9? I'll talk about that. All right, we'll talk about that. What else? If I plug in -1, very similar thing here. If I plug in -1, I get 3 to the -1 power. All right, that is 1 over 3 to the first power. Okay, figure out what the top and bottom are equal to, and we get 1/3, which is already in lowest terms as well. All right. Anything to the 0 power is equal to 1. Anything to the 0 power is equal to 1. So if I plug in that x equal to 0 into the exponent, we get 3 to the 0 power. That's the reason why you always have a y-intercept of 1. It's because the y-intercept is when the x is equal to 0. And whenever you plug x equal to 0 into this, it makes the exponent 0, and then the answer will always be 1. All right, and that's why. If I plug in 3, I get 3 to the first, which is, of course, 3. And if I plug in 2, I get 3 to the second power, which is 9, right? Okay. as you can see here, the 9 is kind of big, and I kind of talked about this when we were doing quadratic equations, I believe, where, and if I didn't talk about it, I'll talk about it now, but I know we didn't actually. So let me just go over that carefully. We've got 5 points here, right? We already know what the shape is basically going to be. The 5 points are just going to kind of help us. So if you've got 1 point, like 2, 9, since 9 is a big number, if there's only 1 point that does that, you guys, you don't have to plot that point. As long as you plot the other ones, I'm okay with that. Don't skip more than 1 point. They'll get you at least 4 points, but if you skip the 1 out of the 5 points, that's okay. So let's plot the other 4 points here. Again, that's if the number's really big and you're like, oh, I don't feel like, changing the scale. You don't have to if it's just 1 point. So 1, 3 is right there. 0, 1 is right there. And then notice 1/3 and 1/9. What are those numbers? You put those in your calculator, they are 0.1 and 0.3. Okay, as we talked about in the parabola section, all right, 8.3, we talked about how if you get a decimal that is 0 point something, that means it's between 0 and 1. So it's going to be really, really close to the x-axis when it's 0 point something. So just get it as close as you can there without actually touching it. Remember, it's not supposed to touch the x-axis, these graphs that we're talking about right now. And then also 2, 9, just make it pointing in that direction. You don't have to plot 2, 9. Okay, I said you didn't have to plot it, but make sure it at least points in that direction in order to be accurate. Okay. And now draw a banana shape, just like we talked about, and make sure it does not, because it's one of these basic b to the x graphs, make sure it does not hit the x-axis. Okay, some graphs we see later on the backside of the worksheet might hit it, and I'll tell you why when we get to it, but don't let it hit it. Okay, just get as close as you can without touching it, and do not let it loop back around. Remember, this banana shape that we've been talking about, you guys, okay, is supposed to go up on one end and what? Down on the other. It does not loop back around and come back up again. All right? So have it get as close as you can to the axis without touching it, but don't let it loop back around. All right? It's going to go up on one end and down on the other. That's how these graphs work with b to the x. All right? Another thing also is make sure this thing doesn't loop back. All right, as we learned back in chapter 2, that'd be a violation of the vertical line test if it looped back like this. All right, because then it wouldn't pass the vertical line test. And these things are all functions. All right, it says y right here, but that's the same thing as f of x. They're all going to be functions. Okay, anyway, all of these b to the x graphs are. They're supposed to pass the vertical line test, so be careful of that as well. All right, but up on one end, down on the other. All right, and in the case of these graphs, we'll see an exception to this here coming up at the end, but these basic b to the x graphs, you guys, it's always going to go up real fast and down almost flat. Up real fast, down almost flat. All right, this next problem here, and we're done here because we got our arrows, we did our shape, okay, we made sure it went through all of our points. It followed all the characteristics that it was supposed to, the banana shape, up on one end, down on the other, all that stuff. So we're done with that. In the next problem here, we have, again, they want us to do the same 5 points. If I plug in those same 5 points, let's start out with 1/3 to the -2. We also learned in chapter 1, that same section I was referring to just a few minutes ago, where you had the exponent rules, we learned that when you have a fraction taken to a negative power, section 1.6, you can, to make it easier on you, you can flip the inside of the fraction and make the -4 positive simultaneously. That's a rule that is allowed to be used. And so that's going to make this a lot easier to figure out, because this would then become 3 over 1 on the inside, and then this now becomes a positive 2. And we know that this is 3 squared, isn't it? Because 3 over 1 is 3. And so that's going to be 9. So what would we get if we plugged in negative 1 into x? Same thing, but now the exponent becomes positive 1, right? And so that's going to be 3 to the first is 3. Anything to the 0 power is 1. If I plug in positive 1, I get what? I get 1/3 to the first power. Anything to the first power is itself 1/3. And finally, what do I get if I plug in 2? I get 1/3 to the second. What happens when you have a fraction taken to a positive power? You take the top to that power and the bottom to that power, and it creates a brand new fraction. 1 squared and 3 squared gives me 1/9. We also did that in section 1.6. Okay. You notice something interesting about this problem compared to the last one? Let's compare it. Notice how the y values are exactly the same, but they're the opposite direction. Okay, 1/9 to 9 from the bottom to the top. Now over here it was 1/9 to 9 from the top to the bottom. It's the same 5 numbers, but just going in the opposite direction. That's the reason why the shape is still basically the same here, but it goes the opposite way. It's because the y values go the opposite way. Okay, 1/3 is going to be this one, all right, as you can see right here, just like this one was for 3 to the x, which is what we just did in the first problem. Okay, so let's go and graph this, and you'll see that it goes the other direction. Again, you don't need to do the one with the 9 there. Just have it point in that direction. Let's plot the other point. So negative 1, 3. Right there. 0, 1. 1, 1/3. 1/9. Remember, 1/3 and 1/9 are just, they're 0 point something. So just get them really close to the axis. They have to be between 0 and 1 since they're 0 point something. And so just get them really close to the axis because it's going to get close to the axis here anyway for this shape that we have up here. Okay, so just do that and you'll be fine. And then draw your banana shape. Again, what does a banana shape do? It goes up real fast on one end, and it goes down almost in a flat manner eventually on the other end. Don't let it loop back upward at all. See how I didn't touch the axis there? Okay, your arrow can touch the axis. Your arrow can even go over it. That's okay if the arrow does. It's just pointing. Okay, but the actual graph itself, not including the arrow, don't let that go over on the other side. All right, not on the other side of the x-axis. And so we did it. We got our 2 arrows. It's going up fast on one end, down slow on the other, down flat on the other. Okay, that banana shape that we need. And don't let it touch the what? Don't let it touch the asymptote, which is, in this case, is the x-axis. All right. Last one here, and then we'll see some different stuff on the back here. 2 to the x. Which we're going to use this answer, that the answer that we get in this problem, we're going to use this a lot on the back side of the worksheet. What do we get for 2 to the x? 2 to the negative 2 power. Isn't that 1 over 2 squared? Just like we had 1 over 3 squared in the first problem. And so that's going to be 1/4. And if we plug in negative 1, a similar thing occurs. 2 to the negative 1 is 1 over 2 to the first, which is 1/2. Anything to the 0 power, when you plug the 0 into the exponent, is going to be 1. Plug in 1, you get 2 to the first. That's equal to 2. You plug in 2 right here, you get 2 squared, which is 4. So because of the fact that it's the 2 is bigger than 1, it's going to be a very similar looking shape to the first problem, 3 to the x, but it's going to be a little bit wider. Okay, it's not going to be so narrow and sharp turning and all that. Okay, I'll show you that here. No big numbers on this one, so I can plot all 5 of them this time. Again, the 1/2 and 1/4, if you put those in your calculator, you might already know what they're equal to. But if you put them in your calculator, they are 0 point something. And so, again, just get those points since they're 0 point something for y. Just get them in between 0 and 1 right there. Just don't let them hit the axis. And we draw our banana shape again. Okay. Up real fast on one end. Down real slow, almost flattening out on the other. Like that. You can see that if you look at problem A and problem C, the shapes are basically the same, but this one is a little bit wider out, isn't it? Whereas this one is a little bit more narrow. Okay, narrow and turning real sharp upward, right? Okay, that's the difference. But it's the same basic shape that I was talking about. All right, so that is what it looks like when you just have x as your exponent and you just have the constant base, no other stuff on that side of the equal sign. And then on the other side, you either have a y or an f of x, which are both representing the same thing anyway. Okay, so now as we move over to the back side, all right, I want to talk about a few things here first. Actually, you know what? Let's go ahead and look over there, and we'll kind of look at both things at the same time here. I want you to notice a few things here. First of all 5 of these problems here have 2 to the x in it, or some variation of that. Okay, right here. We just graphed that just a moment ago. All right, and what did we get? Because I want to look at this here. What 5 points did we get? Because we're going to use these. We got these 5 points. I'm just going to transfer them over to the back side of the worksheet here so we can look at them. Okay, you also have them in front of you there on your own worksheet. All right. So there's my 5 points right there. Again, same 5 points on the front side. I just transferred them over. Okay. Here's how this works. If you have the same exact graph right here, the same exact function, but then you add something to it, and it has to be a constant number, and that's all it's going to be. I'm not going to say plus 3x or something like that. If they add a constant number, or if they subtract a constant number, what ends up happening is, and it says this on the front of your worksheet, okay, if they add or subtract something to the entire thing, okay, the graph is still going to be the same exact looking graph, same exact thing, okay, not wider or more narrow, but exactly the same as 2 to the x, except for it's either going to shift up or down. So if it's plus 3, it's going to shift up. If it's minus, what was that problem right there? Problem E, yeah, it's minus 1. Okay, so minus 1 is going to shift down. Okay, so the graph is literally going to move, but its shape will not change at all. Okay, that's how that works. Now, if you have inside of the exponent plus 3 or minus 1, see how we have that here in the third and fourth problem? You add 3 to the exponent and you subtract 1 from the exponent. See the difference there? The plus 3 and the minus 1 are inside of the exponent instead of being behind the entire thing there. Okay, when that happens, as it says here on your directions here, then the graph shifts either to the left or to the right. Okay, believe it or not, it's actually going to shift to the left when it's plus. You would think it would go the other way because we think of going to the right when it's positive because the x's get bigger when you go to the right, but that's not how it works with the third and fourth one here. It actually does the opposite thing. Plus means left, minus means right. Okay, and then this last one here, when you have a negative 1 times b to the x, or in this case, negative 1 times 2 to the x, all right, that's what this means when the negative is at the front of the expression on that side of the equal sign. It means this right here. When that happens, the graph actually flips over. I'll show you that here coming up, but it's a reflection across the x-axis. That simply means that it flips over to the x-axis. And I'll show you again what I mean by that when we get to it. All right. So, but there's some other things we need to consider here within all of those directions. All right. But again, what does this say? This says shift up. This one says I'm just following the directions on the front of the worksheet. This one's down. This one, remember when it's inside the exponent, plus means to the left. And this one is to the right. Okay. And then this one what? Flips upside down. Okay. So, how do we do all this? What you do is, if it shifts up, think about this for a second, you guys. If something goes up or down, since the y-axis is going up and down, only the y's are going to change. The x's are not going to change at all. The y's are the only thing that's going to change when it goes up or down. So what I want you to do is I want you to picture the original graph here for 2 to the x. It's right here. And just take those 5 points right there and literally move them up. By just count up 3. 1, 2, 3. 1, 2, 3. Move them all up 3 straight up. Don't move them left or right at all, because that would imply that the x's are changing when it goes left or right. All right, because the x's go left and right. Just have them all go up by 3. So you take these original 5 points right here, move them up by 3. Let's see how that looks. And you can use these points here as a reference. All right. So let's talk about that. So the 4 goes where? Let's start out with the bigger number here first. It doesn't matter which one you start with first, though. The 4 will now go up to, let's count this. 1, 2, 3, 4, 5, 6. And so there's 7 right there. And so that would now be there. The x is still 2. So the 2, 4 is now, and you don't have to write this down, but just to help you get used to this, the 2, 4 is now 2, 7. The 2, 4 is now 2, 7. The 1, 2 is now 1, 5. In other words, the y, because you're going up, the y values increase when they go up, because that's in the positive direction for the y-axis. The y values increase by 3 while the x's don't change. And so there that is right there. 1, 5. How about 0, 1? 0, 1 becomes 0, 4. Again, the y increases, all right? The x doesn't change because you're going straight up. All right, anytime you go straight up on a graph, y's are increasing, the x's aren't doing anything. They're just staying, the number for x is going to stay the same. So that point is right there. Okay. And then what about 1/4 and 1/2? I'm not going to make a big deal. I don't care if you add the fraction to the 3. All right. Like I said with the parabola problems, if you end up with a number that's not a whole number, which you will when you add these fractions to 3, you add 3 to these fractions, like we've been adding 3 to these ones right here. If it's a number that's not a whole number, I'm okay with you approximating just when we're doing x, y values on an x, y graph like this, with an x-axis and a y-axis. Not at other times do I want you to round off, okay, like I've said before, unless you're told to. But here it's okay. So 1/4, if you make that into a decimal, that is 0.25, and then this one is 0.5. If you add 3 to that, that's going to be, and we really don't need to approximate this time, but we could. All right. Have at least one decimal place, so if you are going to round off. So if you want to say 3.3 right here, you could. All right. But that way you know what it's between. You know that since it's 3 point something, it's between 3 and 4. All right, so these two values, the x's stay the same. These two values here are going to be between 3 and 4 because it's 3 point something. And so just make sure that when x is equal to -1 and x is equal to -2, that it's between, the y is between 3 and 4 right here, like that. Okay. And you can see that the shape is what? It is similar to the shape that we had right here. Okay, it's just that the whole thing just shifted up. It's like you took the banana and you pushed it upward without changing its shape at all. Okay. One other thing I really want to make clear, you guys, when you go up or down, okay, when you go up or down, the asymptote is moving too. All right, the asymptote moves as well. I need you to, since it's no longer, the asymptote is no longer going to be the x-axis because it's going to move up, I need you to put a dotted line right here. Don't make it a solid line. Asymptotes are not allowed to be solid lines, all right, because they are not part of the graph. That would imply, a solid line would imply that it was. It's kind of like that axis of symmetry thing that we did in 8.3, where I made it a dotted line. Okay, remember those, which was optional, all right, but we put that there, but it was meant to be a dotted line because it is not a part of the graph. It's just something that you use as a guideline to help you graph. Same thing here with the asymptote. Here's the thing, you guys. Do you need to put the dotted line there? On the test, whenever I test, just like you've seen my graphs before, when we graph lines, there's grid lines, okay, that are already on there and that look similar to the x-axis already. So you don't need to make it into a dotted line if the grid line is already there at y equal to 3. Okay. Just make sure, and this is the key thing, just like before, make sure that the graph does not cross over the asymptote. By the way, why did it end up here at y equal to 3? Well, since it was at y equal to 0, right on the x-axis, it makes sense that since everything else increased by 3, that the asymptote should also move up by 3. Okay, from y equal to 0 up to y equal to 3. And that's why I moved the dotted line there. So you don't need to put the dotted line there as long as you don't let the graph cross over wherever the dotted line would have been. All right, I'm fine with that, but just make sure that it doesn't cross over. And so there you go. That's the same exact shape as we got for the 2 to the x graph that was, again, on the front of the worksheet. All right, right here. It just shifted upwards by 3. This problem right here is going to do exactly the same thing, okay, except for it's going to go down. That's the only difference. All right. And also it's only going to go down by 1, all right, because it's -1, not -3. So this one went up 3. This one's going to go down 1, all right. This one's going to go left 3 because it's x plus 3. This one's going to go right 1 because it's x minus 1. And then I'll get to that flip upside down thing here coming up after that. So in problem E right here, we are going to go down 1. And so when you go up or down, you guys, again, the x's don't change at all, but the y's do. And so since it's going down 1, we're going to decrease all of these by 1. So you're going to say 0.25 minus 1, 0.5 minus 1, 1 minus 1, 2 minus 1, 4 minus 1. All right. Just like it says -1 right there, that makes sense. So the x and y's, and again, you don't need to write down the x's and y's here for the shifted graphs. You do need to write down the x's and y's for the original graph because you got to have numbers to start with. All right. And we already had those numbers from the front side of the worksheet, so we're good. But I just write these down here just to make sure that we're getting it in the right place. But all I care about is once you graph the original graph on the front, all right, which you did with the 2 to the x, all right, just take those points and literally physically move them either up 3 or down 1 or left 3 and all that kind of stuff. All right, I don't care if you give me the exact numbers over here. I just do this just as an additional thing, just to be, just as a check, just to check to make sure we're in the right place. 0.25 minus 1 is negative 0.75. Okay, again, you don't have to do this. All right, this is just as an additional thing. But I subtract 1 from each one of these, and these are the 5 y values I end up with. But ultimately, you take the graph on the front, again, this graph right here, and you physically move the 5 points that I plotted straight down by 1. Where do those 5 points end up if I do that? Okay, let's talk about that. There's 2, 3 right there. Originally was 2, 4, so it went down by 1. 1 comma 2 on the front side of the worksheet, so it went down by 1. Now it's at 1 comma 1. 0 comma 1 on the front side of the worksheet, it goes down by 1. Now it's at 0 comma 0. Okay. And then these other points here, remember, it is negative 0 point something. Negative 0 point something for y means that it is between 0 and negative 1. Like that. Okay. Where did the asymptote go? Well, just like it shifted up by 3 over here, it's going to shift down by 1 here. Because everything else shifted down by 1, why wouldn't the asymptote do the same? All right. Like that. And so just make sure that the graph looks exactly the same as the original 2 to the x graph, but it just what? It just shifted down by 1. Okay. Same exact graph. Don't let it cross over that asymptote. It looks like I just barely hit it right there. And like I said, I won't mark you down if you do that. Just don't let it completely cross over it. Okay, as you can see, it's kind of hard to avoid touching it sometimes. All right. What happens when it shifts to the left or to the right? I want you to think about that for a second. If we go back to the original graph, the asymptote is the x-axis, isn't it? The asymptote is the x-axis. If we shift this graph either to the left or to the right, okay, isn't it true that the asymptote, when it shifts to the left or to the right, since it already is the x-axis, which goes from left to right already, okay, what's going on is that it is, it's not changing at all. All right? It's still going to be the x-axis when it shifts to the left or to the right. All right? It's still going to be sitting on the same thing right there. It's kind of like if you had a banana on wheels, okay? It's kind of a silly example, sorry, but the point is if you have a banana and then imagine that it's on wheels right there and it's on the ground, pretend like the x-axis is the ground, all right? If you're going back and forth, the banana is still just as close to the ground as it sits on the wheels as it originally was. All right, and so that's what the asymptote measures. It measures how close it is to the ground, or how close it is to itself, how close the graph is to the asymptote. That's what the asymptote measures. It makes sure that the graph doesn't cross over it. So since the banana is just moving left or right, it's still going to be just as close to the x-axis as it originally was. And so the asymptote should not change when you shift the graph either to the left, like we will in this problem, or to the right. So I just want to make that clear. The asymptote only changes, you guys, when you go what? When you go either up or down. Left or right, it's just the asymptote is just kind of sliding along like it's on wheels. All right? Instead of going up or down. Now, when you go left or right, since that's related to the x-axis, the x's now will change. So when the x's are from negative 2 to 2, what we do, since it goes to the left, that means that the x's are going to decrease. Because remember, the left is in the negative direction. So what we got to do is we got to take our original x values and subtract 3. So negative 2 minus 3. Negative 1 minus 3, 0 minus 3. Again, you don't have to write these down, but it just, like I said, it's a good way to check to make sure. What's important here is that and by the way, the y's do not change when you go left or right. Just like the x's did not change in that previous set of problems, the y's don't change now when you go left or right, because y's change when you go up or down, because y-axis goes up or down. So the y's did not change, the x's did. You can go ahead and plot these, but you could also just what? You could also just take the original graph on the front side of the worksheet and just simply physically move the 3 points to the left, okay, by a distance of 3, and it will give you these same 5 points even if you don't actually write down these numbers, okay? So we got what? We're going to go all the way over to negative 5 now since we went over to the left. And put my y marks on here as well. Okay. And here are those 5 points right here. Okay. So it's going to be, again, the same basic shape, but it just went over by 3. Here it is. Okay. And so we moved to the left by 3. When we move to the right, same thing. The asymptote does not change, so it's still the x-axis on both problem G and on problem F, like we said, but it goes to the right one. What happens when you go to either the left or the right? It's the x's that change because the x-axis goes from left to right, okay, and the y's don't. So if we're going to the right, and again, I know it says -1, just like over here, I know it said +3, but you got to subtract 3. It just does the opposite thing when you got the exponent. All right. So with the exponent, you got to do -3 if it's +3. With the here, since it's -1, you got to add 1 to the x's. Okay. So it's going to be -2 + 1. -1 + 1, 0 + 1, 1 + 1, and 2 + 1. Okay, I took the original x values again and I added 1 to that. So with the exponent, you do the opposite thing. You're going to add when it says minus. Okay, when it's one of these original 2 problems again, where you add or subtract to the entire thing, not to the exponent, but to the entire thing in the back of it, then you do the same sign. If it's plus, you add. If you subtract, or if it's minus, you subtract. The y's again stay the same. Again, it's optional to write these down. What's important is that you physically take the graph on the front side of the worksheet and you move it to the right one. Every single point, okay, needs to move to the right by 1. And when you do that, what does it look like? 2, 4 becomes 3, 4. On the front side, we have 1, 2. It is now 2, 2. On the front side, we had 0, 1. It is now 1, 1, and then so on. And then these last 2 points also. Let's go ahead and graph that. Again, same basic shape. It still has that same banana shape where it goes up fast on one end and it goes down flat on the other. Okay, it's just that sometimes the points move and sometimes the asymptote moves as well, as we talked about. But it has that same basic shape. Up fast on one end, down flat on the other. Okay, this is the exception to that as far as that up on one end, down on the other. Okay, this is going to be a little bit different. When you flip upside down, what happens is this. Notice on the front side of the worksheet, I talked about how -2 to the x is the same thing as -1 times. It's the same thing as -1 times 2 to the x when you have -2 to the x written like this with no parenthesis there or anything, okay, like you sometimes have with exponents. That means that we're going to multiply the y values by -1. We're going to multiply the y value because the original y, which is the same as the original f of x, was b to the x. And so if we say -1 times b to the x, it's like you're taking the original function, which is the original y values, and you're multiplying them by -1. And that's the reason why we go like this. We're going to take the original y values up here, and we're just going to change the sign of them, because that's what happens when you multiply by -1. It just changes the signs of these things, okay, like this. Same exact 5 numbers, except for their different sign now. Multiply by -1. The x values stay the same in that case. And what this does is it creates this effect where the thing flips over, okay. Oh, sorry, that came off the screen there. There it is right there. Okay. So if I plot those 5 points, all right, and again, you don't have to write down these 5 points as long as you remember that just the y values change their sign, and then you do have to plot the points, of course. You got to put your 5 points in the correct place on the graph. You just don't have to write down these numbers as long as you remember that in this case, the y values just change their sign and the x values stay the same. Okay, so same thing as I've been talking about. You don't have to write down the actual numbers when you do one of the shifting graphs. You do have to do it, like I said, when you have the basic 2 to the x graph, all right, because you got to have something to start with. But not on the shifting graphs. So here we go. There's where those 5 points are. Okay, and that's the same 5 points that you'd get if you just simply changed the signs of the y's, okay, and kept the x's the same. We draw the same shape. Unlike all the other graphs we've done, though, this is the one exception to this idea that it goes up fast on one end and down slow on the other. This one goes down fast and up slow. It goes down fast and up slow. So this is just in this example right here where you have -1 times the original 2 to the x function. That's the only time that it does this. All the other functions are going to go up fast and down flat. Up fast and down flat. This one does the opposite thing. All right. And so what I typically do on a test question, you guys, and you'll see this on a similar thing, not the same thing, but a similar thing on the homework, is that I will first of all, when I ask a question, I will ask you to graph the basic graph first. It may not be 2 to the x. It might be 3 to the x or 4 to the x or 1/3 to the x. I'll ask you to graph that basic graph first. We know how to do that now when it's just b to the x. And then right next to that, I'll ask another question where I'll say, graph one of these things right here, and I'll make it the same original function. Like if I say in the problem, if I said on the first part, I said f of x equal to 3 to the x instead of 2 to the x. Say I did 3 to the x instead on the first part. I would then on the second part go something like this: 3 to the x minus 1 or 3 to the x plus 3. And then what you would do on that second part is you would just have to figure out how it shifts, and then you would draw it. Okay, you don't have to write down the numbers on that second part, just on the first part when you do the basic graph, whether it be 2 to the x or 3 to the x. So that's an example of what I usually do on a test. On the homework, if you see the 9.1 homework, they actually ask you to put both the original graph and the new graph on the same XY grid. Please don't do that, you guys. That's messy. All right, I don't know why they ask that. It makes it hard to read, hard to see. Okay, please do, when they ask you, for example, and you'll see this in the homework, it'll say, hey, do the 2 to the x, and then it'll say in the same problem, do 2 to the x minus 1, or it'll say 2 to the x plus 3. Please do 2 separate graphs, you guys, when you do that, so that the 2 graphs don't collide and it makes them hard to read. All right, do them in 2 separate graphs. Don't do it like they ask you to do it. You just have to do the 2 graphs there on those. All right, but please do them separately. That's like right near the end of your homework assignment for 9.1. All right, speaking of that, you'll notice down here in these last 3 problems, this one right here stems off of 3 to the x, which was problem A on the front right here. So what you do on that problem that I just looked at is you don't have to redo the numbers, you guys. Take these numbers that you already have, take these points that you already have, and what are we going to do with those? Because it says plus 2 on the outside, not in the exponent, but on the outside, it means that we're going to what? We're going to go up 2, aren't we? Okay. How about here? Well, this one stems off of what originally? Because it says 1/3, okay, as your base, it's going to stem off of this one right here, problem B on the front. So you take these 5 original points right here, okay, you don't need to write them down again, okay, you take those 5 points again, you take those 5 points and you just what? Because it says minus 1 inside of the exponent, you're going to go to the right one, okay? You're going to go to the right one when it's minus inside the exponent. And then finally here, this is the one where you take, again, the 3 to the x problem from the front, and because it says 3 to the x with the minus in front of it, you take that 3 to the x problem and you multiply the y's by -1, and it's going to make it flip over. So please try that right now. When you're done doing that, we'll take a look at the answers, and then you can hit the play button and you can see that. Okay, let's take a look at number 1 right here. And because it goes up 2, all right, you just take the same 5 points that were on problem A on the front, and you just physically move them up by 2. You don't need to draw, like I said, you don't need to write down the actual numbers in a chart on the side like we sometimes do. Just physically move them up. But remember that what also moved? The asymptote also moved. The asymptote always moves when you go up or down, right? Okay. If you do prefer to find out what the y values are equal to, you just simply add 2 to the y's that are on the front of the worksheet. Okay. And it gives you the y values you see here, 11, 5, 3, and so on. All right. And that is number 1. All right, but you just need to physically move them up by 2. Here again, what do? We move to the right. Okay, by 1, but you're not doing that off of this graph, off of the 3 to the x graph. You're doing it off of the 1/3 to the x graph on the front side. So if I take that graph that was in problem B on the front, 1/3 to the x graph, and you actually go to the right one, you physically move these points to the right, this is where they're going to end up. But remember, when you go left or right, the asymptote is still the x-axis, you guys. It is still the same. Okay. The asymptote is also the same when you do when you have that problem where you have negative b to the x. Okay, because when it flips over, the asymptote is still the graph is still getting closer and closer to the axis. It just is getting closer to it from the bottom end of the x-axis instead of on top of it. Okay, so if you multiply those problems in problem A on the front, because this came from 3 to the x, you multiply those y values by -1, and keeping the x's the same, you get -9, -3 instead of +9, +3. All those y's change by multiplying by -1, and it causes the graph to still be a banana shape, but it now flips over. Okay, and that's number 3 right there. Okay, so remember to have your arrows on both ends as well. It has that banana shape. Okay, and with the exception of a problem like this right here, it's always going to go up fast on one end and down flat on the other. Okay. And as always, just like with parabolas, it's got to be smooth, you guys. No sharp turns or anything. A nice smooth turning movement on these banana shapes. Just like a banana is smooth, right? Okay, you don't have any sudden sharp edges on a banana when you go from one end of the banana to the other. All right, same idea. Okay, so that concludes section 9.1. As usual, let me know if you have any questions about that section or anything else in this packet, and take care. Have a nice day.